Okay, this is our Ruyer reading group. We are continuing our reading of Neofinalism, and I forgot to check what page we were on before we started, so sorry, I'm just gonna skip ahead to see if I can identify that. Bottom of 60. Okay, let's take a look. Yeah, that looks right to me. Okay. Yeah, okay, bottom of page 60 in the translation. Yeah, so we're continuing our reading of the chapter The Brain and the Embryo. So this is one of his sort of like, I guess, core like analogies in this book is that the development of the embryo of an organism, so how it starts off as this sort of undifferentiated blob of jelly or whatever, and then turns itself into this structured organism with different types of cells, different tissues and organs, and so on. This is analogous to the way that the brain of this organism, or in the case of animals, how the brain sort of turns itself into this structured entity that can perform all these different functions. So yeah, the each of these processes is a process of sort of self-structuring or developing into a structured whole that has these different elements that perform different functions. And so he's interested, one of the sort of key concepts that he's interested in here is the concept of equipotentiality. So this is something that in early 20th century embryology was presented as sort of a key finding about the development of an embryo. So there were all these experiments. I think sea urchins were sort of like the favored model organism for this. But if you take an embryo early enough in the developmental process and you do certain kinds of intervention on it, like you remove a section or you take you cut pieces off from the left and right and swap them and so on. These different types of interventions don't change the sort of overall structure of the organism that develops at the end. So even if you swap left and right in the embryo, the organism still develops looking like a normal sea urchin or whatever it is, rather than having left and right sides sort of swapped. Or maybe it's better to another organism that they used was like frogs. And so like you could remove the portion of the embryo that normally would develop into the left leg and put it on the right side, and do the same thing with the right leg onto the left side, and those portions would develop into the appropriate leg for where they are, rather than the leg that they would have developed in if the would have developed into if that intervention hadn't happened. So you don't end up with a frog with a left leg on the right side, for example. And so yeah, so what this shows, or the sort of interpretation that was given at the time, is that there's some sort of like top-down direction of the development of the embryo. So it's not that this specific portion of the embryo is sort of pre-programmed to develop into a left leg. It's that somehow the location of this portion of the embryo relative to the whole embryo sort of determines it to become a left leg. And then if that portion through as a result of this intervention ends up being on the right side instead, then that sort of top-down direction will make it develop into a right leg. And yeah, so this of course is dependent on the timing of the intervention. So if you do it early enough, then you can get a normal looking tadpole at the end of this developmental process. But if you start making these interventions later in development, then at some point that undifferentiated portion of the embryo has undergone differentiation so that it is no longer capable of becoming either a left leg or a right leg. It's sort of decided that now it's a left leg, and it can't sort of undo that decision. But yeah, and then there's sort of like a branching structure where like maybe at one point it has determined itself as a leg, but not as a left or right leg, and so it if you move it to like I don't know where the eye is, it won't be able to develop into an eye. But if you move it from left to right, it's still capable of sort of making the correct leg based on what side it is currently located on. So anyway, there's a sort of like branching differentiation that happens in the development of the embryo, and so this is like an important sort of set of experiments for Ruyer because it shows that you can't really explain development in terms of like a pre-existing structure that would be there from the beginning of the developmental process. You're sort of what you're trying to explain is precisely the fact that you end up with a structure, and so you can't sort of assume that the structure is already there or that some like meta structure is there to guide the development of that structure. And so there's a kind of yeah, self generation of the structure in a way to sort of reliably produce the normal form of the tadpole at the end of this developmental process. And so he's going to use this as an analogy for how learning happens, that we are capable of sort of producing structures within ourselves through processes of learning in the same way as the embryo is capable of producing structure within itself through the developmental process. Okay, so yeah, we can pick up from the bottom of page 60. So he's just gone through some of these arguments, and he's going through the next bit that we're going to read is about some of these proposed explanations for equipotentiality that try to sort of explain away the apparent equipotentiality in terms of like some sort of mechanical process that would be there from the beginning. So we can pick up from the bottom of page 60, please.
I can read. The first one is A, quantitative explanations. There is an ordinary, quote-unquote, equipotentiality in countless adult tissues. We can live with a single lung, a single kidney, and even with a fragment of a lung, which is in this sense equivalent to the whole. Because the result of Lashley's experiments is expressed quantitatively, quote, the performance deficit is proportional to the quantity of the damaged cortex, unquote. The explanation seems to emerge quite naturally from the facts. The case of the cortex would be similar to the case of the pulmonary or renal tissue. The cortex would act, quote-unquote, massively. But this is obviously pure wordplay. The equipotentiality of the pulmonary or renal tissue has nothing to do with the brain's equipotentiality. The effect, oxygenation or chemical purification, is directly measurable. In contrast, a behavior or the solution of a problem is not itself quantitative. The illusion stems from the fact that the deficit of a behavior can be estimated by indirect means, the time required, the number of errors, etc. The weakness of so-called holistic biological theories, or of numerous Ganzheit-Theorie proposed recently, derives precisely from their conflation of the whole as, quote, quantitative mass, unquote, and the whole is a domain of forms capable of self-survey, and thereby of equipotentiality. There is in reality nothing extraordinary about the qualitative equivalence of the part and the whole in a quantitative mass. We can sweeten a glass of water with 1 or 2 pieces of sugar. The quote-unquote holists sometimes seem to believe, as a result, that there is nothing strange in the fact that a single blastomere engenders an entire embryo, that a single cerebral hemisphere accomplishes the same work as the 2 hemispheres, or a fragment of a sensory area the work of the intact area. It is clear that the quantitative theory sidesteps the following problem. An adult organism is structured as a whole. A sensation or a behavior is equally structured in this way. How can an overall structuration be independent of the spatial support in which it is realized? Half a piece of sugar is still quote-unquote sugar, because in sugar, nothing more than an indefinitely repeated molecular microstructure is at issue. But half a vehicle is not a quote-unquote vehicle. The striking thing is that half a newt or urchin gastrula is sometimes not only still quote-unquote newt or quote-unquote urchin, but a whole newt or urchin. Similarly, half an auditory or premotor zone is at times an integral instrument of complex and structured sensations and behaviors. With damaged retinas, I can have quote-unquote vision, and we are used to estimating the residual vision to 1 decimal point. But the problem is that I recognize the same forms when I see them with different or more or less extended parts of my retina. The contrast with what a photoelectric screen would produce is the heart of the matter. So as I understand the argument in this section, Ruyer is saying that equipotentiality is not just a matter of kind of quantity of brain tissue. And the point is that the same form can be instantiated in a significantly reduced quantity of brain tissue, or, as he says, I can recognize the same forms visually, even if my retina is damaged. So it's not the material quantity that explains the instantiation of the form, because even with significantly reduced quantities, the form is still instantiated, even if it's a bit weaker.
Yeah, so he's criticizing this sort of confusion between a quantitative what we could call maybe a quantitative equipotentiality. So the fact that like the example of the kidney. So yeah, you can live with one kidney, so therefore the two kidneys are sort of equivalent to the one kidney. And here, of course, there's a quantitative difference that, like, your ability to remove toxins or whatever from the bloodstream is going to be lower with one kidney than with two. And it's just that the amount of like the degree of purification that you can do with one kidney is sufficient for like normal sort of everyday life purposes that you can get around fine with just one kidney. And it's clear that the sort of equipotentiality that's exhibited by the brain is not a purely quantitative equipotentiality in this sense. So, like, the capacity to solve crossword puzzles, or I don't know, identify faces or whatever. Like, you can sort of come up with a quantitative measure that how much time it takes to do something, or what percentage of errors you make or whatever. But the actual task itself is not quantitative in that sense. And of course there are many different tasks, like even a portion of the brain that is sort of specialized for some like visual perception function. Of course there are many like different types of things you can do visually. You can identify faces or shapes, or distinguish light and dark colors and so on. Like all these different elements, all these different sort of functions are all sort of intertwined together. And so how do you, like, if you wanted to turn it into like a number, how would you sort of weight one of these functions against another? That, like, okay, you're like 10%, you make 10% more errors than an average person in face recognition, and 5% more errors in I don't know, identifying geometrical shapes. And how do you like add those two sort of quantities together to say that your vision as a whole is X% worse? And yeah, so this is a clear sign that there's two different sort of kinds of things going on when we're talking about the fact that you can live with a single kidney on the one hand, and the fact that someone with certain brain injuries can still perform certain functions on the other hand. And so, like, what he's or his sort of analogy here is how sugar, for example, if you take a sugar cube and dissolve it in a glass of water, you have a certain quantity of sugar per I don't know, cubic millimeter of water. And if you take another glass of water, the same volume, and you put half a sugar cube in it, you'll just end up with a concentration of sugar, that's half as much. And so this is a purely quantitative one. And in this case, the sort of quantitative nature of this comparison between the two glasses of sugar water is just a result of the fact that sugar is the same in both cases. It's the same kind of thing. There's just more of it in one case versus the other. And then on the contrary, you have like a vehicle or a car, for example. Half a car is not like just a lesser quantity of car than in the first place. Like, the full car allows you to drive, and the half car doesn't really allow you to do anything. And so it's clear that the cognition case is closer to the case of the car. Half of an ability to recognize faces is not really anything. It's not like just a lesser quantity of ability to recognize faces. But what he points out here is that what's sort of like the striking finding is that even cases where there is pretty extensive damage to the brain results in people who do have a capacity to recognize faces, for example, maybe much lower or with more errors, but they still have that capacity. And so even though it's not a purely quantitative difference, the result of this sort of equipotentiality in the brain is that sort of damage to the quantity of brain volume that is sort of dedicated to this task can still leave the person with the sort of overall capacity, even if with more sort of difficulty or greater degree of error or something like that.
Yeah, I was wanting to follow up on that idea of quantification here, because he says right above this section we started today, he says it pretty clearly. He says self-survey is just another way of denoting and defining equipotentiality, and self-survey is clearly an important concept in his work. So that's what he's talking about here. So this idea, like you were saying, so in equipotential domains or domains of self-survey, you can't directly quantify the outcome. You can only quantify the secondary outcomes, versus non-equipotential domains where you can directly quantify. For instance, in lungs, the oxygenation of the blood, or you can quantify kidney function and stuff. So, is this kind of a central component of domains of self-survey, is that they can never be directly quantified?
Yeah, that's an interesting question. I don't know if you'd want to take this as like a sort of criterion or like a test that you could say, okay, this whatever, entity exhibits self-survey because it is not directly quantifiable or something like that. I think like maybe the examples even of the lung and the kidney are probably more complicated than he's presenting it here, because I mean a kidney, for example, is capable of removing different substances from the bloodstream, not just one specific substance. And so, it could be the case that, loss of a kidney or damage to the kidneys makes it, less capable of removing substance A from the bloodstream, but doesn't have any impact on its ability to remove substance B. And then so the question would still be like, how do you weight these two sort of functions of the kidney and come up with an overall number and say like kidney function has declined by X%. The case of the lungs, like maybe it might be more straightforward because I think the sort of carbon dioxide and oxygen sort of function is sort of relatively straightforward. But yeah, so it might be like it might not really be possible to sort of state that like this organ or this entity, whatever it is, either is or is not quantifiable. It might just be like, yeah, a question of how much you're losing by sort of reducing by sort of assigning a measurement to the activity of this entity. That like, yeah, in the case of the lungs, maybe you don't really lose that much by just saying, the lungs are capable of oxygenating X, volume of blood per minute or whatever. Maybe in the kidneys, you lose a little bit more by sort of reducing it to a single number. And then, of course, like we talked in a previous session about all the many problems with something like IQ as like a sort of measure of, yeah, VO2 max exactly for the lungs would be like a good measure. But yeah, so in the case of like cognition, if you try to sort of reduce human cognitive ability to this one number IQ, there's a lot of problems with that. And yeah, so maybe it's more a sort of evaluation of like how much information, how much sort of richness of structure are you losing when you try to express the capacities of this entity in terms of a single number. And yeah, so that would be like to some extent like a judgment, a question of judgment. How much sort of important information have you lost? And then also it would be a sort of a question of degree rather than a yes or no, because you might have, some entities that you can sort of reduce to a number without losing much information, and then others that would be maybe more information. And then some cases like, the human being as a whole entity, of course, if you try to, just sort of assign a number, say this person's like effectiveness is 25, and this other person's effectiveness is 36, like that number is not going to tell you very much about what that supposed effectiveness means.
Yeah, yeah, it's interesting. I'll kind of hold that in the back of my head as we move forward. I can read the next part if everyone's ready.
Maybe just one comment before we go on to the next bit. So I would add that, like, in the case of a human being, of course, we do have various, measuring sort of practices. Like I mentioned, the IQ test, and there's similar sort of standardized tests that are used for like education, SATs and so on. Um, and then there's like athletic competitions where you're sort of measuring people relative to each other in terms of some sort of, whether it's like speed running a certain distance or whatever. But I think what's sort of, well, for one thing, of course, we have many different measures of human performance depending on different domains. Like one person might have a great SAT score but be terrible at running, and vice versa. And then whether the SAT score is more important than your speed at running a marathon is obviously a question about like what for what purposes you're doing the measurement. But then also in general, the sort of like social implications of that measurement, like I think we would generally take it as like having the capacity to decide on what gets measured is sort of like an important sort of aspect of social power, that like deciding that people will have to write an SAT to be able to get into this prestigious university, for example. You're sort of like deciding that this specific measure is what we care about, and is going to sort of allocate social roles to people based on this measure. And I think in the case of humans, part of what we mean by this sort of like self-survey capacity, or this sort of self-generation, is that there's precisely this ability to sort of refuse a measure or to contest a measure or something like that. So you can, as a person, say this SAT score doesn't sort of like reflect my I don't know, intrinsic worth as a person, or my ability to run a marathon or whatever it is. You can sort of say that you can contest the validity of this measure. You can sort of pull back and look at the measure and say, how much is lost by reducing this person to a measure. And so that's part of, I think what he's talking about in the case of self-survey. I mean, obviously he's not talking about you can strike the phrenologist, the classic Hegel thing. You can refute phrenology by cracking the guy's skull. But yeah, so like obviously the embryo is not sort of like telling the embryologist that that your quantitative measure is wrong. But I guess part of what makes the embryo capable of that self-survey is that maybe in sort of normal circumstances a certain measure is adequate, but then if there's some sort of intervention or abnormal circumstances, maybe the embryo does something different where that measure doesn't really apply. And so it's this sort of capacity to adapt in a way that is not reducible to that one measure that I think is sort of characteristic of self-survey in general. And in the case of humans, it can be like an explicit sort of contestation or rejection of a measure.
Yeah, that's interesting. As you were saying that, and I was starting to sort of type this out, but the way as you were saying that, and kind of looking back at the book, this idea of direct or secondary. So for instance, going back to the lung or the kidney, so you can directly measure the function of a lung. You can measure blood oxygenation, so you can see the degree to which it's working more or less, and say a kidney as well. Maybe you could measure the clearance of a specific toxin or something. But with the brain, you're measuring behavior, but you're measuring an outcome of the behavior. So the behavior is still present, and you can't. It's kind of, I don't know. I'm sure people would debate this, but you're not directly measuring it. I mean, that's what you were saying. And what he says here about vision is interesting too, because he talks about, so when you have damage to the retina, although you can measure, as he calls it, residual vision to 1 decimal point. I suppose like talking about your vision on a Snellen chart or something. He says you can still recognize the same forms, even with reduced vision or whatever. And this is contrasted to a photoelectric screen, where if you had damage to that, the same form would not be produced. So that would be the direct measure. And I guess he's saying, your the acuity of your vision is a secondary measure. So, but yeah, that's
Yeah, I guess like he maybe thinking of some of the like early sort of pattern recognition type of devices that were around at this time. So like you have like an array of pixels, I don't know, 10 by 10 or whatever it is, and if a certain sort of segment, a certain set of those pixels are, illuminated, for example, it will sort of detect the pattern and say that's a letter A or a letter H or whatever. But then if you sort of, deactivate some of those pixels and you make them unable to respond, then it will no longer be able to recognize a letter A or a letter H or whatever it is because the pattern is no longer there. I mean, this is a sort of very rudimentary kind of pattern recognition that he's talking about here, because of course you can contemporary like the things that we have today, you can often have systems that can recognize a shape, despite noise of some kind, like some sort of disturbance to the image. And this, of course, is why we have these like captchas with all these weird like extra lines, and the letters are on different angles and so on, because it's trying to sort of go a little bit beyond what computer vision systems are capable of doing. Although I think most of those are actually beatable today by computer vision systems. It's just that it's not really worthwhile to do it at a large scale. But yeah, so the systems that he's talking about are very sort of brittle in the sense that a small disturbance like breaks its whole capacity to recognize a shape, whereas the ones we have today are much more robust in the sense that they're capable of still recognizing the shape despite a lot of disturbance, in the same way that a human, of course, can recognize a letter A even with all kinds of lines, or the picture is blurry or whatever. And this is sort of analogous to the way that a human who has suffered a stroke or damage to their brain in some other way is often still capable of recognizing letters, for example. But yeah, so I guess like the relationship with like the quantitative element is that yeah, what you're, so as you were saying, yeah, it's a sort of indirect measure. You can say like, how many errors does a person make on a certain like standardized letter recognition task, and you could sort of quantify their visual ability in that sense. But the task itself is not quantitative because it's like recognizing these letters. But yeah, so I think again you would have to understand it in terms of like how much information are you losing by reducing the ability to recognize letters to, say, like number of errors, because you could also do a different measurement of like how much time it takes, and then it would be a question of like, how do you sort of weight errors versus time, that like if you take 3 hours to identify a letter, but you have 100% accuracy, like that's still not exactly the same performance as a sort of normal person that can recognize the letter within seconds, but with maybe a little bit less than 100% accuracy, et cetera. So like, how do you sort of weigh these different measures against each other and say that like the sort of total vision capacity is X% of normal?
Okay, I guess I can go ahead and do the next section. I think I'll read B through D, and then we'll have E left to finish this section out. So B, global psychological or physiological explanations. Very different in appearance. They are similar, in fact, to a quantitative explanation. They appeal to a general factor such as quote unquote vigilance, proposed by Head. Physiologists who object to the use of a psychological notion in this situation and always replace it with quote unquote scientific equivalents, such as the threshold of excitability or any general factor. But just like the first explanations, these ones also fail to address the essential structural problem. It is perfectly possible that the notion of vigilance responds to something significant. Every human being has the experience of states of mental stupor when he sees without seeing. A cortical lesion can determine this state of general stupor fairly well. Yet this stupor, or this increase in the threshold of excitability, or this loss of mnemic availability, can only mask the effects of equipotentiality. It is not enough to appeal to its opposite, vigilance, to have a positive explanation of equipotentiality. Let us add that we do not see how this explanation would apply to embryonic equipotentiality. See pure Gestaltist explanations. They have had enormous success in both embryology and psychology, precisely because they seem to tackle the right problem of the conservation of structure, no longer the conservation of a constitutive microstructure, but of the structure as a whole, despite the quantitative decline in the material support for this structure. If I cut in half a magnet, a soap bubble, or a capacitor charged with electricity, I would still structurally have a magnet, a soap bubble, or a capacitor in which electric charges are distributed in the same way as in the original capacitor. This time the case is apparently similar to the cutting of an egg, a gastrula, or a cerebral area in half. But as we have seen, the analogy is more ostensible than real. According to this principle of least action, the Gestalt form that conserves itself from a dynamic equilibrium, operating step by step and leading to very simple, homogeneous, and maximally symmetrical structures. As P. Weiss, Humphrey, and others have stressed, behavior often progresses toward symmetry, homogeneity, and harmonious and well-connected lines. But it would be truly difficult to see the progress of organization from the egg or the blastula to the adult, progress toward symmetry and homogeneity. The regulations after lesions and the various regenerations take place through complex reshufflings and through the intervention of various tissues, which produce appropriate neoformations, or through buds of regeneration, along with work of specialized cells that had first to migrate to the right place. We need a great deal of good faith to believe that they can be explained by a spontaneous dynamic rebalancing like that of electricity in a capacitor. In general, the transfer of a behavior or a habit after lesion is a much more complicated phenomenon than a simple transfer of forms onto a reduced material. It is almost always accompanied by appropriate and significant qualitative modifications. In an old experiment of Lashley, reported by Humphrey, a rat trained to cross a labyrinth that included left turns underwent an operation that made it impossible for it to turn left. The rat nevertheless succeeded in crossing the labyrinth by turning 3/4 of a turn to the right, which replaced a 1/4 of a turn in the opposite direction. Lashley's postoperative rats are occasionally forced to cross the labyrinth by crawling on their front feet, by performing somersaults, and so on. The pure connectionist explanations. They are practically ruled out by the very nature of the problem, and in any case, they cannot be applied to embryonic equipotentiality unless the preformationist explanations in embryology are equated with the connectionist explanations of cerebral behavior. The facts cited previously against pure quote-unquote Gestaltist explanations are much more decisive against pure connectionist explanations. If a pure Gestalt transfer poorly explains the creativity of the rat who makes 3/4 of a right turn to replace the 1/4 of a left turn, neural connections established by learning would not explain it at all. None of these studies of learning or retention of the mazes after brain lesions has given the slightest indication that the maze habit is composed of independent associational elements. There was never amnesia for one part of the path with retention of another. When a mother sends her child to deliver a letter to the neighbor, she expects him to go through the back door if the front is closed. By the same token, a sheepdog gathers the flock at the signal of his master by taking into account the arrangement of the sheep and the nature of the terrain. In these cases, Humphrey notes, beyond the various terminal connections implicated in the preformed action, there has to be a more general neural pattern that activates the particular pattern of actions. I need to kind of look back over this really quickly, but just the big picture I'm kind of taking here is he's pointing out that that there is, as he was saying earlier, there is some sense to this activity, some finalist target, but how that is achieved is not just a purely like mechanical, isn't underlined by a purely mechanical, say, restructuring of the physical aspect, or the physical part that underlies this behavior, and nor is it just like a single way to go about achieving this end. So
Yeah, I think the item C is probably the most important one here. The pure Gestaltist explanations. So this is like sort of a recurring motif in his work that we saw many times in the cybernetics book as well. That he thinks that these sort of Gestalt explanations are better than some of the other ones, but are still insufficient. And a lot of these explanations had to do, or they sort of took an analogy with a physical process of involving some sort of like a field or something along those lines, and took that to be sort of an explanation for these sort of holistic processes in human or animal behavior. And so one of the sort of like stock analogies that they pointed to was like the way that a soap bubble, for example, produces this spherical shape, not because there's some sort of like directing intelligence that like likes spheres or something, but rather because the sphere is the shape that that minimizes surface tension for a given volume. So just by this sort of physical process of minimizing surface tension, you end up with this nice geometrical shape. And then so Gestalt psychologists, of course, were famous for identifying these like tendencies to find these nice geometrical shapes in visual perception, that you can sort of see a circle even if there's no actual line identifying a circle. If there's like certain patterns of white versus black, we sort of like see the circle even though there's actually no circle drawn on the paper. And so they took this sort of like landing on the circle, this nice geometrical shape, as sort of as a result of a similar kind of process as the soap bubble landing on the sphere as a result of this physical surface tension minimization process. And so he gives some similar examples here in this text. So he talks about how so he mentions the soap bubble, but he talks about the magnet, for example, that like if you take a bar magnet that has a north and a south pole, and then you cut it in half, each of those halves will itself now have a north and a south pole. So the sort of polarization, this north-south direction of the magnet, is sort of restructured or reformed after this intervention of cutting the bar in half. And of course, this is not a result of any kind of intelligence that is sort of making the magnet take on this structure. Is a sort of general like physical process that brings about this structured polarization without any sort of top-down direction. And this is an analogy that Schelling loved as well. But Ruyer points out that this sort of undirected formation of a structure, the polarization of the magnet, is something very different, or the example of the soap bubble as well, is something very different than the formation of an embryo, in the sense that each of these sort of Gestalt processes are sort of a return to equilibrium, or seeking equilibrium in some sense, like the minimization of surface tension, for example. You're sort of descending a gradient of surface tension until you reach a minimum, and then it just sort of stays there. Whereas in the case of an embryo that is undergoing differentiation, it's you have to sort of twist the meaning of a word like tension or something like that to a pretty unrecognizable degree, to say that an embryo that is turning into a tadpole is sort of minimizing tension. And especially when you do things like these interventions like swapping left and right or whatever, the sort of adaptation of the embryo to that to respond to that intervention is it's very hard to describe that as a kind of minimization, where you have like as you attach the limb bud to one side of the embryo, then the nerves grow towards that limb bud, as he mentioned in a passage we read a few weeks ago. so the organism or this sort of embryo developing undergoes these complicated processes that involve adding new structures and more differentiation and so on. It seems like it's almost the opposite of this sort of like descent to the lowest degree of tension, like in the case of the soap bubble. So yeah, so these types of and then he talks about for example like the rats that figure out that they can, even though they can't turn left anymore, they can do 3 right turns and bring about the same result. Like if you try to describe this as a minimization of tension, you're again sort of like twisting the meaning of the word tension beyond recognition. So it's pretty clear that there's something different going on in the case of the rat that turns right 3 times to substitute for a left turn than in the case of like the soap bubble that minimizes tension and produces a sphere. Yeah, so there's some discussion in the chat here about how this would sort of compare to Simondon's account of individuation, and I think he actually, if I remember correct, I can't remember actually which, it might have been in the more like psychological parts that we've read from Simondon. He talks about how like migratory fish, for example, are sort of pretty hard to like the fact that this fish might migrate many thousands of kilometers to return to its spawning grounds. It's pretty hard to describe that as like a sort of reduction of tension operation. So in certain cases, like certain very immediate perceptual performances, or like the animal that sort of like is drawn towards a food source, for example, you can describe this in terms of like a minimization of tension of some kind in a relatively straightforward way. But many behaviors of animals are much harder to describe in those terms. And he talks about those migratory fish, or any sort of animal performance that is not like very directly tied to something that it's perceiving right now. These kinds of behaviors are much harder to describe in those terms. And yeah, in general, he talks about how vital individuation would be a kind of slowing down of physical individuation. So like the brick is a sort of stock example of physical individuation, or the crystal. In these cases, it sort of takes on the form at one point in time, and then just sort of stays there. It doesn't do anything further without any sort of further intervention. And this would be sort of comparable to the minimization of tension explanation that the Gestaltists are using, but because the vital individuation process does not just result in this like minimal tension or minimization of some quantity, it means that you can't sort of understand it in those same terms as just like a minimization of some quantity that sort of brings about an equilibrium state and then just stays there.
The thing I find interesting about this section is that he's using some of the same examples that Merleau-Ponty used in Structure of Behavior, about the the rats in the maze, for instance, and Lashley's point that the rat doesn't forget portions of the maze. It's sort of the form of the maze is a whole, I guess, for the rat. But I think that this would be, the fact that they're drawing on the same studies, I think will make it easier to try to align Ruyer and Merleau-Ponty, and to try to see where, because Ruyer talks about a much broader variety of forms. In Structure of Behavior, Merleau-Ponty is just concerned with humans and non-human animals, and doesn't talk about embryology at all, as far as I remember. So yeah, it may be interesting to kind of see if Merleau-Ponty's conclusions can be extended to some of these other forms that Ruyer talks about.
Yeah, so this is maybe one of the sort of like key differences between what Ruyer is doing and what Merleau-Ponty is doing, in the sense that Ruyer of course is very interested in embryology, and he sees the formation of the sort of biological formation of the organism as already a kind of quasi-psychological process. I guess like the way he would, a sort of careful way of presenting it would be to say that the same types of sort of taking on structure and self-survey and these things are going on in the case of the formation of a biological organism, and then in the learning and adaptive performances that organism is then capable of doing. And of course, Ruyer will even go on to ascribe similar sort of true form properties to fundamental physical particles as well, which I don't know if Merleau-Ponty would follow him along those lines, but so he's willing to extend a lot of these arguments to domains that Merleau-Ponty doesn't really talk about, at least in structure of behavior, and I think also in phenomenology of perception. There may be he does have a lecture course on philosophy of nature that I haven't read, so it could be he might sort of engage with some of those topics there. But in the sort of the better known works and earlier works, he doesn't really engage with those topics at all, really, as far as I remember. Okay, we can go on to the next bit. I can read this. Yeah, I think maybe we have like 2 more portions to read. Okay. Item E, explanations by gestalt and connections. Virtually every author falls back on a combination of the 2 preceding theses. The general pattern Humphrey refers to would be a gestalt form, dynamic and transferable, which would thus set varied connections into action depending on the circumstances. By combining 2 bad theses, the author hopes to generate a valid one. Equipotentiality would mean a 2-stroke regulation. 1, a simple dynamic regulation of the type of physical regulation through the establishment of a gradient or of a self-distribution would, 2, entail a change in the effectors used. This dualist theory can be adopted for the explanation of embryonic equipotentiality. It is enough to replace the neural connections with the genes that are thought to contain the explanation of the structures. In this case, the gradients of the chemical substance provide the general pattern. Depending on the local level of concentration, the genes that are triggered at different thresholds engender this or that organ. When the experimenter cuts a T gastrula in half along the sagittal plane, the gradient regulates itself at first like electricity in a capacitor. Then the affected genes generate, according to new thresholds, other organs than those they would have produced, with a similar overall form but different dimensions. Child, Dalek. The great success of gradients in animal and especially plant biology stems from the fact that they explain the adaptability of organic formations. And here there's a table, so a 2x2 table. So general pattern, gestalt corresponds to chemical gradients, and then determined neural connections corresponds to genes. So this is the correspondence between embryology and neurology, I guess. Okay, picking up the text again. Kafka and Levin adopt this dualist theory under the name of the theory of the, quote, circular process, unquote. When an animal approaches an attractive prey or flees danger, the neural effectors that enter into play can be very varied, but they are controlled by a simple dynamic situation, by the increase or decline of tension resulting from the approach or moving away of the danger or the goal. The, quote, circular processes, unquote, are analogous to feedback systems whose significance in modern machines as well as in physiology has been underscored by cybernetics. In these systems, an obtained first effect reacts on the subsequent affection, which thus takes the result into account. Finally, Lashley also adopts this dualist theory. Consider, for instance, a relative discrimination learning in rats. The animals learn to react positively to the most brilliant or the greater of 2 circles, regardless of their absolute brilliance or magnitude. Pure connectionist theories already fail to explain this learning. They also fail to explain the conservation of this habit after a lesion of the visual cortex. But if we suppose an S gradient along with which an equilibrium between he's referring here to a diagram, which I'll get to in a second. Okay. But if we suppose an S gradient along which an equilibrium between the P's and N's, whatever they may be, is established, it will be the global equilibrium on the S line that determines the activation of the R path or the L path, and not the fact that the stimulus is P rather than P prime or P double prime. Okay, so how to describe this? Okay, so we have a horizontal line, and then there's 2 vertical lines stemming from that horizontal line. One of which is labeled R and the other is labeled L, although right and left seem to be swapped here. I guess we're looking at it from a perspective of an organism facing down on the page. And then above the R line, there are circles labeled P, P prime, P double prime. And then above the L line, there are circles labeled N, N prime, N double prime. And there's no S on the diagram, but I'm assuming that S is supposed to be quantity that would vary along the horizontal line. And so the idea here, I guess, is that rather than saying that like the choice of R versus L is sort of triggered by the presence of P or N, what instead we have a sort of a two-stage explanation where there is some quantity S that is different along this horizontal line, and these items or these stimuli P or N sort of induce some or correspond to different degrees of this quantity S, and then depending on where this stimulus lands on this S gradient, then it triggers either the R or the L response. So this sort of two-stage explanation with a gradient and then a set of responses is supposed to sort of overcome the difficulties of either the purely sort of gradient explanation that the Gestalt people were using, or the sort of set of pre-existing responses explanations that you find in some of the like the reflex theory people that we were discussing in the Merleau-Ponty reading. Okay, I think I'll stop here. It's kind of a awkward place to stop, but there's no real stopping point here. Yeah, and so this is a sort of a combination, a combined sort of mode of explanation. So you have a two-stage explanation with a gradient and a sort of set of pre-existing responses. And this, like when he talks about embryology here, I think this is sort of like the default mode of explanation of embryology or developmental biology today, is that you have these sort of chemical gradients that define, say, like the head versus tail axis of the embryo, and then you have various genes that are expressed at different rates depending on the interaction with these chemical gradients, and this is sort of like the general pattern of explanation for within developmental biology today, that you have these genes that are already there, these sort of pre-existing structures, and then you have a gradient or probably several gradients that sort of regulate which genes get expressed where, and this sort of combination of these two elements of explanation is supposed to be able to account for like these equipotentiality phenomena. So the fact that you can like divide an embryo at an early stage and get two sort of normal looking tadpoles that just are a bit smaller, or that are smaller than the normal tadpole, but are still tadpole shaped rather than like a front half tadpole and a back half tadpole. So he's going to go on and criticize this this sort of hybrid explanation in the next bit, but we haven't seen that criticism yet. So I don't think there's too much to comment on in this passage, unless anyone else has other comments.
Nothing else from me. I can read the next section. Did we leave off at this critique?
We are at these explanations fare no better.
Okay.
And you can read to the end of the chapter. It's like almost 2 pages. I guess.
Okay. Yeah. These explanations fare no better than the preceding ones. We have already shown at which point the genes in embryology are incapable of fulfilling the enormous task assigned to them. The theory of the circular process contradicts the facts. The animal that flees or approaches does not resemble a body that obeys a difference of potential and field. Kohler's own observations and those of Guillaume and Metterson on chimpanzees clearly show that the intelligent solution struggles against the direction and attraction of the goal, but not like a force that can be represented by a vector. In a detour, the part of the trajectory that distances the animal from the goal has to reverse the quote-unquote circular process. So to explain why the animal persists in this provisional direction, we have to assume that the parts of the trajectory that distance it from the goal are balanced by the parts of the trajectory that bring it closer to this goal, in the same way that the ascending part in a siphon is balanced by the descending part. But unlike what happens in a siphon, in the animal's detour, these parts of the trajectory are crossed at different moments. Cerebral dynamism, if it exists, is thus altogether different from a physical gestalt dynamism, where the forces that balance one another are all equally present. Something in the field of consciousness or in the cortical field of the animal has to temporally and spatially survey the entire trajectory for the dynamically opposed parts of this trajectory to be maintained because of their sense, meaning, in parentheses, relative to the ideally projected and not yet realized total path. The finalist direction of trajectory has to struggle against the direct dynamic tendency to move in the vectorial direction of the goal. This is even clearer in the case of a more complex behavior. When a chimpanzee nibbles an overly wide board to thin it down and turn it into a stick, in what way can a quote-unquote circular process explain this long and arduous action? How can a quote-unquote circular process explain a political or military human maneuver that is intended as a bluff or a provisional concession? Here the notion of dynamic equilibrium is just a metaphor of doubtful interest. An equilibrium between senses, meanings, differs radically from an equilibrium between physical forces. This latter equilibrium has a unique outcome in which the constitutive vectors are combined. In contrast, an equilibrium between senses, meanings, keeps distinct the various senseful actions that have to be composed, and this is why these actions can be ordered in a series. This critique applies to Lashley's schema. The schema is vaguely plausible only for the particularly simple case of discrimination between relative degrees of brightness, and one must not examine it too closely, because a discrimination, like a trajectory with detours, implies that the animal keeps distinct the terms to be discriminated, and does not operate like a scale whose needle only indicates a difference in weights. Besides, it must be that Lashley was not satisfied with this explanation, because he ultimately replaced it, while remaining within the framework of dualist theories, but abandoning the identification of the general pattern with a gradient or a dynamic equilibrium, with a curious quote-unquote wave theory of learning. The cortical surface is equated with a continuous network, association fibers being so numerous that the influxes can practically diffuse in all directions, like the surface of a pond on which stimulating or inhibitive wave trains propagate, trains that conserve some measure of the stimuli's form while moving in the cortex and combining with other wave trains. The figures formed in this way can be instantaneous or stationary, like those of the vibrating plates sprinkled with sand and excited by a bow. This wave model would show that the cortical responses do not depend on points stimulated in the receptive areas, and, on the other hand, that a fragment of the cortex can function in the same way as the whole. Because this theory would not in any case account for embryonic equipotentiality, we need not discuss it. It is doubtful that it constitutes an improvement over its predecessors. If the pattern of stimuli is conserved intact in the wave trains, then is there a significant difference between this theory and the connectionist explanation? If the cortical waves modify this pattern, they can only render it rougher, but cannot extract its thematic character. And the difference between this theory and the hypothesis of dynamic rebalancing would this time be insignificant. Lashley seems to forget that the essence of equipotentiality does not reside in the circulation of forms from one point to the other in the nervous system, but in the thematic equivalence of forms. This theory's main interest lies in showing the hopeless state of deterministic theories of equipotentiality. And that's the end of the chapter. As with the rat maze examples, this is another phenomenon that Merleau-Ponty discussed in Structure of Behavior. These detour behaviors where an animal has to temporarily move away from a goal in order to navigate some kind of obstacle and ultimately arrive at the goal. And I agree with Ruyer that these phenomena would be pretty difficult to explain in terms of sort of a gradual release of tension as the animal gets closer and closer to the goal. And it seems reasonable to suggest, as he does here, that the animal has some sense, some survey of the whole action that it needs to take, so that, it in the moment can know that, or have some sense that it needs to sort of move away from the object that it wants to get to in order to get to that. And so there's this, kind of a transtemporal action that it has in mind and then executes. And this we've talked a few times over the course of this reading group about this idea of like sense as having a kind of melody structure. And he doesn't talk about that. He doesn't talk about it in those terms here, but it seems like a good way to describe what he's describing. That each action in this series of actions in the detour that needs to be taken sort of makes sense as part of this larger context of sense in the way that a note in a song sort of makes sense or is heard as the note as which it's heard because it's part of this melody and not a different melody.
Yeah, I think the sort of key feature that he's criticizing these like gradient or field sort of explanations, whether sort of in the pure form or in these hybrid forms, is precisely that the field or the gradient has to be present. It has to be like there at that moment for it to be able to sort of guide the animal or to guide the development of the embryo or whatever it is. And so this is maybe useful in certain cases where there is like a very like there is a sort of structured situation where the animal is sort of moving towards this goal point that you can sort of represent in terms of a minimization of tension, but it is precisely for that reason inapplicable to cases where the goal state is not present or there isn't like this sort of linear approach to the goal state that the animal can perform. So like in the structure of behavior, he goes through some of these different types of experiments where animals have to take a detour to get to the goal state, usually food, of course. And he talks about how in some cases it seems like the obstacle to the animal performing being able to solve this kind of problem is not so much a cognitive one of like not understanding the situation, but rather a sort of affective one in the sense that the animal can't like bring itself to move away from the goal state to to perform this detour to get to the goal state eventually. Like you have food, one of the examples he gives is a sort of a maze that has like a spiral shape and a cat navigating this maze. And so if you put the food at the center and the cat at the outside, the cat has to go around this spiral, and so at certain points it has to move away, or at least in a sort of tangential direction to the from the food. But each sort of turn of the spiral brings it a little bit closer to the food, and the cat is able to figure this out and successfully navigate the maze to get to the middle and get the food. But if you do it the opposite way with the cat in the middle of the spiral and the food at the outside, then each turn of the spiral means that each sort of furthest point from the food in each spiral is further and further away, rather than getting smaller and getting closer and closer. And in this case, the cat ends up like not really being able to sort of not being able to like figure out or to successfully navigate the spiral, because it sort of gets stuck at like the close point of the spiral, the point in a certain loop of the spiral that is closest to the food, and then it can't sort of bring itself to execute another loop that takes it further away from the food, even though that is the only way for it to actually get out of the spiral and get to the so in this case, like of course maybe other animals like maybe I don't know, a monkey or something would be able to perform this task, but it's doing so precisely by sort of increasing the tension of this sort of like direction towards the food at each loop of the spiral. So it has to be able to somehow like repress this draw towards the food, this kind of like attraction that the food exercises, that you could represent in this like vectorial sort of field term. So it has to be able to sort of act against that gradient of attraction towards the food. And precisely this kind of capacity is something that you can't really explain in terms of like a sort of very straightforward sort of gradient field type of explanation. And of course, humans, like he talks about these things like performing a certain action as a bluff to I'm going to do this so that my opponent thinks I'm going in this direction, but I'm actually going to go in this other direction. Like these kinds of things where there's like this complicated sort of reasoning process behind the the decision for one action versus another. This is like pretty like if you were to try to represent this in terms of a gradient and reduction of tension, you would kind of empty that notion of a gradient and tension of any sort of discernible meaning. And so things like a bluff or a provisional concession are his examples, but anything that involves like representing a goal state and a means of getting to that goal state that is not like a linear reduction of the distance between the present state and the goal state. Like anything that involves sort of provisionally moving away from that goal state as a way of getting to that goal state indirectly, it's hard to represent that in terms of this gradient and sort of reaching a minimization of tension. This last bit, the last bit where he talks about Lashley's sort of like other explanation, this like wave theory, is interesting because there's actually a sort of framework for computation called a reservoir computer, which is precisely used in certain, like there are neuroscientific approaches that sort of use this framework to sort of represent what's going on in human and other animals' brains. So it involves like sort of representing an input as a wave that would sort of operate on this. You can think of it as like a bucket of water kind of picture, that like there's a wave front that sort of bounces around within this bucket of water, and then you have some sort of readout that sort of takes this wave and reads it as like a number or something like that. And of course, you can have multiple different waves within the same bucket of water, and they would sort of interfere with each other in different ways. And you can sort of perform computations in terms of how these waves interact with each other. I don't know actually if that sort of representation or that sort of framework of like reservoir computing like is sort of explicitly drawing on Lashley's work, or if it's like an independent sort of reinvention of the same idea. But it's definitely, Ruyer sort of dismisses it fairly quickly here, but probably if he were writing this book today, he might look at it more carefully and sort of give a similar type of argument as he does with in the case of the Gestalt theories, that like this is interesting and useful for certain cases, but it doesn't really solve the more fundamental problem of how this sort of absolute survey happens. Okay, so I think we can stop here since we're at a chapter break anyway, and then we'll pick up at the start of chapter 7 next time. Okay. So thanks everyone for coming out, and hope to see you next